Morning, guys. I'm doing okay. We're about halfway on the food drive, okay? So we have about 80 items or so. So as you bring them in, you have until March 25th. Just bring them on in, okay? You can also bring them by my office, so you can bring them to class. I wanted to, I'm not going to hand back your test today. I'm sorry. It'll be next week before you get it back. I'll almost certainly get it back to you on Tuesday, and I'll post it on the internet as well. But I do want to just go over your grades. And I just want to remind you how your grades are calculated, and just to remind you where the weights follow, where they fall. So remember, you have 5 quizzes, each count 100 points each, and then you have a 200-point final and a 200-point project. And then with this food drive, that could be up to 20 points extra credit, which I imagine y'all get in the end. All right. Don't forget that your lowest quiz grade is dropped. I just want to go over this because, yeah. It'll be cumulative, yeah. It'll be taken largely from the old exams, from the 5 quizzes. Don't worry, it'll be fine. You'll be okay. It's worth 200 points, all right? I don't know, Faith. She asked how many questions it'll be. Just a second, Kelsey. I'm not sure. Typically, when I give finals in my classes, I sort of just use the old test, and I take them from the old test. And I might change some wording, but they're largely the same. So I usually advise my students just to study the old test. And usually the averages on the finals is higher than it was on the quizzes because you've already seen all that material. Does that answer your question? And so how long is it going to be? Probably twice a regular quiz, about 30 questions. But remember, you have, what, 2 hours to take it. So, Kelsey? We're not having next Thursday yet. I have a court date. I'm sorry. I can't. I'm a CASA. You know what a CASA is? I have a court date, so I can't switch that. I'm sorry. Let me check my calendar. Yeah, it's next Tuesday, March 26th. There will be no class. And next Thursday, actually, we're not meeting in this room, but I'll send y'all an email out. We're going to meet in Pelcher Hall somewhere. Okay? I'm sorry. What is it, because it's the day before break? I'm sorry. I mean, I never require y'all to come to class, but we're going to have class, and we'll cover new material. Okay? No class Tuesday at all. I'll send y'all an email. It's going to be in a different room, okay? It'll be in Pelcher Hall somewhere, and I'll send y'all an email. Okay. That's right, your progress report. So just a short update on what some of you have been doing, on what y'all have been doing, okay? All right, so anyway, where was I? Did I answer all your questions? Okay. I wanted to go over this because people didn't do so well on that last quiz. I think you probably, like, from what you told me coming out, you thought that was the case. Was it more difficult than the previous quizzes? The worst one yet? Yeah. Okay. Well, it is what it is, but let me just remind you of the layout of the grades and how they're calculated, because it's actually not that bad. So you have these 5 quizzes, and so this student has sort of been doing mediocre, making D's and C's and maybe up to a B on a quiz, a 60, a 70, a 60, an 80, and a 50. And remember, this 50 is dropped. So I just get rid of that completely, and it's like it never even happened. And then your final, this student made about a 75%, and given their performance on the quizzes, that's sort of what I would expect, about a 75% on the final, you know, with proper preparation and what have you. The project, they did a good job. They got almost the full 200 points. If you do a good job on your project, I would fully expect that you get the full 200 points. That carries a lot of weight in this class. 200 out of 800 points, that's 25 percentage points. All right? So the project is really there to sort of help your grade, because I know that not everybody tests very well. And it's also just an opportunity for you to do something that interests you and that you find, I don't know, fun maybe even. And then the extra credit adds another couple points. And so this student it's pretty darn close to making a B. I mean, I can finagle the numbers and get it to come out as a B pretty easily. All right, so if you bomb this quiz, my message to you is don't sweat it too much, that there's a lot of points in the mix, and there's a lot more opportunity to build up your grade. Does that make you feel better? Oh, okay. I'll hand back the quizzes next week, and hopefully go over and sort of find your mistakes and feel better about it. All right? All right, next Thursday, you can go and write this down in your notebook. We're going to meet in Pelcha 219. Next Thursday, we're going to meet in Pelcha 219. All right? Everybody got that? Pelcha 219 next Thursday? And there's no class on Tuesday. All right, guys, we're moving on to Chapter 8. I'll put up the homework for Chapter 8 soon, within the next couple of days. And it's on elasticity, waves, and sound. And we're going to look at a number of different applications for sound and waves and what have you. It's on elasticity, waves, and sound. All right, so if you were to define what is a sound wave, what would you say? What is a sound wave? Just in your own words. What's a sound wave? Sound wave? Anybody? Brittany? Okay, it's sound, right? But what causes a sound wave? Like we experience sound vibration. So a sound wave is really just organized vibration. Right? A sound waves are just vibrations. These vibrations are carried, in this case, from the speakers or from your mouth through the air molecules that are in the room and transmitted to your ear, where it's then converted into an electrical signal of sorts. So these are just really organized vibrations. And in this chapter, we'll look a lot at sound waves, how we can use them, and how they respond in certain situations. Just organized vibrations. The vibrations are periodic. That means they repeat over and over. They have a particular period. Because they are periodic, they repeat. Because they experience a force, that puts them back into place. I'll show you what I mean. This is called a restoring force. When we're talking about sound waves, a nice analogy is of a spring. So for example, here I have a spring, and I can make this spring vibrate. And the reason that it vibrates is because it has this restoring force that's going to put it back to its original position. So right here, this is my equilibrium position for this spring. But if I displace it and cause it to vibrate, then it moves up and down. And the reason it moves up and down is because it wants to return back to that equilibrium position. It has this restoring force. What's causing the restoring force? It's the spring, right? It wants to return back to its original position. And so because of the way the spring is made, it has this, what's the word? This physical need, I guess, to return back to its original position. right? So that's just a vibration. We can describe this restoring force by something called Hooke's law. And Hooke's law refers to a whole host of forces, restoring forces. But it just says that the force is equal to negative times k times x. In particular, this is talking about a spring. So let's say that I have a spring here, and I have a block attached to that spring. If I displace this block, if I pull it in one direction or the other, then it's going to feel a force. Can I go to the next slide? Yeah. So if I displace, no? That was a k, right? Yeah, negative kx. That's Hooke's law. So if I take this spring, and I'll say this is my equilibrium position, this is x equals 0, and then I stretch this spring out, pull that mass back, then that mass is going to want to return back to that equilibrium position. And so when you let it go, it's going to oscillate. It's going to accelerate towards the equilibrium position, and then because it has inertia, it has that speed already in place, it's going to go past the equilibrium position, and then it'll come back again. And this restoring force that pulls it back towards the equilibrium position, this is that F is equal to negative kx. K is called the spring constant. And it specifically refers to a spring, but you can also find these constants for other oscillating bodies, even if they don't physically have springs attached to them, like in molecules, for example. They vibrate very much like they're attached to some type of spring, and we can define that spring constant for those things as well. It's really just a constant that's proportional to the restoring force. And so, for example, let's say this spring has a spring constant equal to 100. The units are not terribly important, but it's 100 newtons per meter. And let's say that I pulled it back here to x equal 1 meter. Then the restoring force is negative kx. And so that's going to be negative times 100 newtons per meter times 1 meter. So it's going to have 100 newtons, negative 100 newtons. Notice the negative, it refers to the direction of this force. And since that force is pointing in the negative direction, Hooke's law brings it out to be negative as well. Okay. So you need to have a general understanding of Hooke's law that the force is just proportional to the displacement. David? Right. Right. How much you pull it back from that equilibrium position? Right. And so if you, I think equilibrium, that's okay. Yeah, and if you pull it back further, then you're going to get a bigger restoring force. If you pull it really far away from that equilibrium position, then you'll get a bigger restoring force. All right? And this is a general guideline for oscillating bodies. It doesn't have to be a spring. It can be some other body as well. We have all sorts of oscillating bodies. Like, for example, you can make one at home. Like if I have this meter stick, it has a certain spring-like quality in it. So if I push it down here, it's going to oscillate back and forth because it wants to return to that equilibrium position as well, the equilibrium position being right here. And so if you displace it from that equilibrium position, then it oscillates back and forth because of that restoring force. If you displace it further and further, then it feels a bigger force, a bigger restoring force that brings it back to the equilibrium position. Let's look at, let's imagine like this meter stick, or similarly if you have like a diving board. Say I have a diving board right here with a person on the end. Right, this is their equilibrium position. I'll call this x equals 0. That's their equilibrium position. But then if they push the board down, like they jump up on it and causes the board to push down, what is the direction of the force that the board exerts on the person? Is it going to be up, down, or to the side? The direction of the force that the board exerts. This is the restoring force. It's going to point upwards, right? So that force, this is my restoring force, because remember, it wants to return to that equilibrium position, which is right here. And so it exerts a force trying to get back to that position. And then it comes back up here. Say it returns to that equilibrium position here. At this point, it's coming up in this direction, and then it continues on in that direction. And then so in the fourth step, the board will actually go up here. Now what's the direction of the restoring force here? Up or down? It's going to be downward, because it wants to return to that equilibrium position. Now we can also describe the velocity and the displacement for each of these. So here I have a maximum positive or negative displacement for the diving board. It is a maximum displacement, but is it positive or negative? It's going to be negative because it's down. Here my displacement is 0, and here my displacement is maximum and positive. So if I were to draw a displacement versus time graph, that is just the position versus time graph, here I have negative x max. Here I have x equals 0, and here I have positive x max. So if I were to draw then x versus t, I'm going to start out at x equals 0 right here. That's at this position. And then at B, I'm going to come down here. This is at point B. And then this is C. I'm going to come back here to the equilibrium position. And then at point D, this fourth scenario, I'll come back here. So my graph is going to look like this. If you were to plot out this position versus time, it's going to look something like this. All right. This is a sine function mathematically. It's a trigonometric function. If I were to continue plotting this out, it would look like this. All right, this is point A, this is point B, point C, and point D. So that's my position versus time graph for this cycle of motion, where I start at the equilibrium position in point A. At point B, I go to maximum displacement in the negative direction. Point C, I come here, and then point D, I come back to the maximum in the positive direction. And then if I were to draw a part E, let me go ahead and draw that here. It would just return back to the equilibrium position. Let me show you. So this is E, where it returns back, and that's at this point on the graph, E. This is one full cycle of motion, where it starts at the equilibrium position, it goes to the negative maximum, comes back to equilibrium, goes to the positive maximum, and then comes back to the equilibrium position. So on our spring, what this would look like, what we're getting at here is frequency and period, by the way. On my spring, if I were to think of one full cycle, which would be shown by this. See, I would start out here, then it would go to the maximum negative, it would come up to the maximum positive, and then go back to the equilibrium. So it would look like this. My one full cycle would start here. I'll do start and stop. I'll show you it kind of fast. So, start. Start. Stop. So it goes through one, I don't see that digital. Slow motion. It goes through one full cycle. This is your equilibrium. It goes through the negative. It comes back up to the maximum positive, and then it comes back down to the equilibrium position. One full cycle. Okay? Just like on the diving board. If I were to plot the velocity, which of these scenarios has the maximum velocity? Is it going to be point B or point C? Where does it have the maximum velocity, the guy on the board? Is it when he's at one of the maximum positions or when he's at the equilibrium position? It's at the equilibrium position, right? Because he's coming through that equilibrium position. That's where he has the maximum velocity. You can think about this in terms of energy. Because where does he have the most potential energy? Remember elastic potential energy? Where does he have the most potential energy? At the equilibrium? At point A, he has, no, not A. At B or D, he has the most potential energy. That's when all that energy is pent up inside the board and it's stored there. And so all that potential energy is converted to kinetic energy at what point? What point? Where does he have the most kinetic energy? That is, where is he moving the fastest? At point C, right. So at point C, all of that potential energy has been converted to kinetic energy. So if I were to plot the velocity of this graph, of this scenario, it would look like this. So I have, when I plot velocity versus time, I have positive V max here, or excuse me, or V equals 0 here. When I'm in that fully extended position, I have V equals 0. Here I have positive V max. Here I have V equals 0. And down here I have negative V max. All right, and here I would say that this would be negative V max with the assumption that this guy is in the process of going down. And so if I were to plot the velocity, it would start here, go to 0, go up to positive V max, go back down to 0, and then go down to negative V max. So this would be like point A, B, C, D, and then E. So we can characterize the velocity of the guy all throughout the scenario. And that's true for any oscillating body, whether it be a mass on a spring or be a sound wave or any type of wave, a wave in the ocean. Let's describe some of the characteristics of waves and how we describe them by the frequency, the period, and the amplitude. Are those terms that you're sort of familiar with? I'm sure you've heard frequency before, but what about period and amplitude? Maybe? Okay. It might have been a while. Imagine you did it in like high school physical science. So we're going to describe the rate of vibration by frequency or with frequency, period. This will be T, capital T. Frequency, by the way, is abbreviated with an F, a sort of a script F, and the amplitude. Which I'll describe with a capital A. All right, the frequency is defined as the number of vibrations per second. We use frequency to describe a lot of things that are periodic, not just sound waves and what have you. We'll talk about that. We also use it to describe electricity, like we use in our house. Frequency is the number of vibrations for a given time. So for example here, so if I have, let's see if I can start this. I'm going to count the number of oscillations in a given time. So I have 1, 2, 3, 4 oscillations in about that many seconds. So my frequency would be 4 oscillations per 4 seconds, which would be one oscillation per second. So my frequency is just the number of vibrations per unit time. It is measured in a hertz. The units are 1 vibration per second, which is equivalent to 1 hertz. And this is abbreviated with a capital H, lowercase z, the name of a person. All right, those are the units for frequency. Now, if we take the inverse of frequency, then we get the period. So frequency is vibrations per unit time. And so if we take the frequency of the the inverse of the frequency, that gives us the amount of time for a given vibration. So the period, t, is equal to 1 over the frequency, or vice versa, that the frequency is equal to 1 over the period. All these things are on your equation sheet, but you do need to know how to define or how to figure out what is the frequency and the period for a given wave. And this will come into play when we get into sound waves, because frequency will describe the pitch of a sound wave. All right, so we have these two expressions for frequency and period. What are the units for period? The units for frequency are vibrations per second. Then what are the units for period? It's just seconds per vibration, so we would just say seconds, right? So the units for period are in seconds. And it's just the amount of time for one complete oscillation. The units for period are the second, and this is the amount of time for one complete oscillation. All right, let's do a quick example. A diving board takes 0.08 seconds to make one complete vibration. And when I say that it makes one complete vibration, that means that it starts here at the equilibrium position, it goes up, it comes back down again, continues all the way through, and then comes back to its equilibrium position. So that is one complete vibration. If I were to draw this on a distance versus time graph, it would start here, it would go through the maximum, through the maximum negative, and then come back to its original position. So that is one complete vibration. To start at the equilibrium, to go all the way up, all the way down, and then come back to its original position. And this particular diving board takes 0.08 seconds to make this vibration. I want to know how many vibrations does it make in a second. All right, so if I want to know how many vibrations it makes in 1 second, and I know that it takes 0.08 seconds to make one complete vibration, how am I going to determine that? How am I going to determine the number of complete oscillations that it makes in 1 second? What will I do? Celeste, what will I do? Well, it takes 0.08 seconds to make one oscillation. I want to know how many oscillations in 1 second. Karen? Ruth? Right, I have to make 0.08 seconds 1 second. That's right. How would I do that mathematically? What would I do? Right. I just say 1 second divided by 0.08 seconds, and that'll tell me the number of vibrations, right? How many times does 0.08 go into 1? And what is that quantity that I've calculated then? If I divide 1 by 0.08, what would we call that? Would we call that the period or the frequency? It's one of those. No, it's not the period. It's the frequency. Yes, it's the frequency. It's the number of oscillations in 1 second. It's the period. excuse me, is the frequency. What is the period for this diving board, by the way? No, it's not 1. It's 0.08. That is the period. So the period for this, the time to make one complete oscillation, is 0.08 seconds. So a lot of work in these problems is just sort of interpreting what the numbers mean. The period is 0.08 seconds because that's the time for one complete oscillation. And so the frequency, which is what I want to know, is going to be 1 over the period. That's 1 second over the number of seconds for one complete oscillation. How many times does 0.08 go into 1? Will tell us the number of vibrations per second. And that's 1 over 0.08, which is 12.5. So the frequency of this is 12.5 hertz. All right. Let's say another situation. What if the frequency is equal to 264 hertz? I'm going to write out the units longhand, 264 vibrations per second. All right. What then is the period? Given the frequency, how would I find the period? Now this frequency is much bigger, right, than the other, 265 instead of 12.5. So is the period, yeah, right? Oh, I'm sorry, 264 all the way across. I'll fix it later. So I have a much bigger frequency. Okay, yeah, thank you. All right, thank you. That's a rhetorical question. Yeah. Is the period going to be bigger or smaller than for these others? I have a bigger frequency. Do I have a bigger or smaller period? I have a smaller period. Very good. So if I have a bigger frequency, then I have a smaller period. And so the period here is just the inverse of the frequency. That is 1 over f. And this should be 4. That's 1 over 264 hertz, or vibrations per second. And that gives somebody said already, 0.0038. And that's the period for one complete oscillation, which is just in seconds. So if I'm looking at a distance versus time graph, the same one up here, distance versus time, one complete oscillation goes from the equilibrium to the max, back to the equilibrium, to the min, back to the equilibrium. Then the time for one period is going to be this time. All right? That is the period. Let me ask you another question. Let's say that I plot the distance versus time over a more extended time. So let's say it looks like this. All right, that's my distance versus time for this oscillating mass on a spring or whatever it is that's oscillating. And I want to know what the period is. I'm going to draw it differently now. Is the period the time from here to here? The time from here to here? Or is it the time from here to here? I'll call this A. I'll call this B. I'll call this C. Which is it? Is the period A, B, or C? It is C. That's right. So notice here that I haven't started at the 0 position, but instead I start at some other position, but I still have to go through one complete cycle. I have to go down, back up again, and then back to my original position. All right, so you can determine your period graphically in this way too. And you might see a problem like that on the quiz too, where I just give you a graph of the position versus time and ask you, what is the period? And you can do that just by taking it, measuring the time from the graph. I could take it at any point, right? I could take it, like I could go the distance from here to here. That would be a period. This is a period. I can start from here to here. That would be a period. Starting at one point, going through the equilibrium position once, and then coming back to it again from where you started. Is that clear how to graphically determine the period? All right. We can have, or let's just figure this out. So let's say we want to know the period of a radio wave. And if you look at your dial on your radio, it gives the frequency. In fact, those numbers, when you go through the radio dial, it gives frequency. And so let's say that I'm listening to, I don't know, 98.1 or whatever. That's measured in megahertz. All right, so the frequency of that then is 98.1 times 10 to the 6 hertz. And so if I want to know the period of this, it's just going to be 1 over the frequency. And that's going to be just the inverse of that. 1 over that is 1 times 10 to the minus 8 meters. So that means that in the wave, that the distance between, or excuse me, not meters, but seconds, it means that the time between successive peaks is 1 times 10 to the minus 8 seconds. So this is a much faster wave than anything that we have, these physical waves. We can also have transverse waves. We have two types of waves that we'll talk about, transverse waves and longitudinal waves. I'll show you an example of both. Yeah. Got it okay? All right. Transverse waves. And transverse waves, the motion of the wave is perpendicular to the velocity of the wave. You can see this if you have a rope. Y'all ever had a rope and you just swing it up and down? You know what I'm talking about? We'll do it in a second, but that's a transverse wave. So if you're standing here and you have a rope in your hand and you make a force that's up and down, it creates this wave in the rope. You can actually get a pretty good transverse wave just by shaking the rope up and down. That's called a transverse wave. The velocity of the wave is in this direction, but the motion of the medium in the wave is actually perpendicular. So the motion of the rope is up and down, and that's perpendicular to the actual velocity of the wave. So you actually have this energy that's going in that direction. That's the velocity of the wave, but the actual rope is just moving up and down. So that's a transverse wave. And then we also have longitudinal waves. This is like a sound wave. The motion is parallel to the motion of the wave. So the motion of the medium, which was the rope in the above example, but in this case I'll do it with a spring, is parallel to the velocity of the wave. So here, you can do this with a spring, but instead of going up and down with forces, I'm going to move back and forth, and then I'll get a spring. I'm attached to a spring, and it'll get rarefied in some places and compressed in other spaces. Let me show you. It's kind of hard to draw, but I'll show you. Here we go. This is a slinky. I need somebody to help me. Faith, you want to help? All right. hold this. So I can create both a, let's stay where we are. I can create a transverse wave. I remember in the figure to make a transverse wave, I have to move my hand. If I have to move my hand, so I can make a transverse wave. You cannot make a fast wave, that's the way it is. But that's a transverse wave. If that's but the spring is moving. The spring is moving up and down. Let me let it slow down. The longitudinal wave is harder to make. Let's see if we can do it. So we have to stretch it up really tight. Okay. Ready? Watch close. I see it. There's sort of a transverse and a compressional wave. You know, you get this. Not really, yeah. It's a nice transverse wave. Anyway, that's cool anyway. Is it? Yeah. It's hard to see the compressional wave. Thank you. That's okay, Faith. That's okay. Thank you. So a longitudinal wave, an example of that is a sound wave. This is also called a compressional wave. It's also known as a compressional wave. And the reason it's called that is because the medium is actually compressed, so it'll be stretched out, and then as the wave travels through, it compresses, and then it stretches out again, and compresses, and stretches out again. So it's called a compressional wave. But we can describe the frequency and the period in much the same way, in exactly the same way as the longitudinal wave, as a transverse wave, excuse me. Sound is a longitudinal wave. All right, so what are examples of each of these? What are some examples of transverse waves that you can consider? Like apart from the rope, what are some examples of transverse waves? What? What did you say? Hey, I'm not sure, that's not clear to me. Convection, he said. Waves in the ocean. Yeah, so water waves are a good example of transverse waves. That's really a good one. The rope, you can do the rope. That's all I can think of right now. You don't think of another transverse wave? Caterpillar? Yeah, if you swing it up and down. Yeah. Okay. Anyway, transverse waves, like waves in the ocean. I'll show you an example of that in a bit. Water waves are a type of transverse wave where the velocity of the wave is perpendicular to the motion of the medium. And then the compressional waves, a good example, are sound. It's kind of cool, I think, how we create sound waves. We just have a speaker box. It has like a little membrane in it. It's attached to like an electromagnet that will cause the membrane to vibrate back and forth. So this membrane goes back and forth. This is like a little electromagnet right here. And it causes it to go back and forth. And then that causes these areas of high pressure that come out. So this speaker will boom, 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 like that. And every time it comes out, it pushes the air and causes these areas of compressed air and then areas of low pressure. And so if you were to plot out the pressure versus position, so this will be pressure on the y-axis and then the position on the x-axis. But you could just as easily replace this with time because this wave travels through space. I'm going to have high pressure here, low pressure here, high pressure here, and so it'll look like this. In areas right here, I'll have high pressure, and these areas, I'll have low pressure. All right, so a sound wave is really just these compressed air. Now, there are a few other characteristics of waves that we'll need to know. And we'll use these later in the semester when we go into electricity and light and what have you. The wavelength. This is the distance between consecutive similar parts of a wave. So if I have my person and they're moving their arms up and down and they make this rope, they make this wave in a rope, it's going to be the period will be the position between this point and this point. Or excuse me, not the period, the wavelength. This is one wavelength. But you can measure the wavelength from any position. So for example, I can measure it from here to here. I can measure it from here to here. These are all one wavelength. The abbreviation for wavelength is the Greek letter lambda. So this would be one wavelength. This would be one wavelength. When I say similar, what I mean is the wavelength isn't the distance from here to here, because this is the downside of the wave. This is the upside. The wavelength is from here all the way over to here. So when I say similar, that's what it means, that you're going to a similar position on the wave, all right? Not just to the next position, but the next position that's either up or down. All right, so that's the wavelength. We'll also need to know the amplitude. That's going to be related to the intensity of the wave and the speed of propagation. Let me write speed of propagation first. The speed of propagation this is just the rate of travel, how fast it goes. And I'm going to call it the velocity of the wave. Now, if you remember back from chapter 2, velocity or speed, that's just distance over time. And so distance over time, this is going to be one wavelength over one period, one wavelength over a period. So the period, by definition, is how far it goes in one. The wavelength and the period are by definition related, that the wavelength is the distance that the wave goes in one period. So it's just the wavelength over the period. The velocity of the wave is the wavelength over the period, and this is in meters per second. Wavelength is in meters, period is in seconds. These are all on your equation sheet, so don't bother trying to learn these, but you just need to sort of understand them conceptually. Don't try to bother memorizing them, I mean. So if my velocity is equal to the wavelength over the period, I can write it in this way. And that 1 over the period is also the same as what value? The frequency, yes, thank you. So it's also equal to the wavelength times the frequency. You'll see some homework problems where you're just given a certain wave, you're just sort of calculating these various values, the wavelength, the frequency, and the velocity. As I said, the various equations are on your equation sheet, but you just need to know how to use them. So this is equal to the velocity. Finally, you also need to know the amplitude. The amplitude, this is the height of the crest, maximum displacement from the equilibrium. So on my figure up here, if my equilibrium position for this is right here, my amplitude is going to be this distance. So this is the amplitude. It's just the maximum displacement from the equilibrium position. In the case of your sound waves, where they're pressure waves, that's going to be the pressure above sort of the ambient pressure around the air. How high is that pressure? It's the height of the crest, maximum displacement from the equilibrium, and we'll call this amplitude x because it's really just a distance, right? And it's measured in meters. As I said, we have these for compressional waves as well. Can I go down from here? All right. So we define these for compressional waves in a similar way. If this is my compressional wave, I have these areas of high pressure separated by areas of low pressure. My wavelength would be this distance, the distance between similar parts. The velocity of the wave would be in this direction, and you could find that as the wavelength over the period, or the wavelength times the frequency. All right, and then also the amplitude, which we called x before, is going to be proportional to the pressure. All right, so when I have really loud music, irregardless of whether it's really low pitched or really high pitched, it just means that I have very high pressures that are impinging upon my ears. And the amplitude then is proportional to that pressure. Let's see. All right. Waves carry energy. Can I go down from here? Let me see if I have something first before I do that. I don't think I brought it with me. I did. Yeah, so let's waves carry energy. This is in general true. Whether you're talking about compressional waves, longitudinal waves, or even like electromagnetic waves, waves carry energy. I have a little clip. This is about how, well, I'll just play it. It's a Mythbusters episode, although it's just audio, about how these waves carry energy. It's just sort of for your own interest. All right, guys, so just this general idea that waves carry energy, and they carry energy in a lot of different ways, like with the avalanche or the glass breaking, but also they carry energy into our ears. Like when we listen to sounds, it carries energy into our ears. So as I said, we can see this in a number of different ways. Sound hurting our ears. We'll talk about that in a bit when we get into decibels and what have you in the next class. Sound hurting our ears. We can have waves that erode rocks, like water waves. They carry energy. They crash onto the rocks and erode them. You can have light waves. These carry energy. Like the sun's rays can warm you. They carry energy. And in general, the energy of a wave is proportional to its amplitude squared. So the energy is proportional to its amplitude squared. That means if you double the amplitude of a wave, it's going to quadruple the amount of energy that it carries. So if you double or triple it, it's going to multiply the amount of energy that it carries by a factor of 9. If you spread this wave out over a big area, the energy of the wave will decrease. As the wave spreads out. So for example, if you go to like a rock concert or whatever, where are you going to find the most energy? Right up next to the speakers or far away from the speakers? Where will you find the most energy? Close to the speakers or far away? Right, close. So you don't want to stand right next to the speakers because all that energy is impinging upon your ear. But as you move further away, the energy from those waves is spread out over a larger area, and so it decreases the total amount of energy that actually comes to you. We can describe that in terms of the intensity of the wave. And the intensity of a wave we describe as the energy per unit time, which is something that we'll call the power, divided by the area. So this is power over area is the intensity. So I is equal to P over A. This has units, power has units of watts per square meter. Our intensity, power is in units of watts. It's an energy per unit time. And an area, of course, is in square meters. All right, just one more thing. I know we've been here a lot. I know y'all are tired, but I just want to go over one thing, just a few more minutes. The human ear, we'll talk about it quite a bit next time, how the human ear works and what it's sensitive to. But the human ear can detect sounds with an intensity down to like 10 to the minus 12th watts per square meter. That's an incredibly small intensity for the human ear to pick up, but about 10 to the minus 12th watts per square meter. And it can range all the way up to 1 watt per square meter. So the human ear has this very incredible range where it can pick up these very small sounds and then also still detect these very large sounds. Now we can create devices to detect either one of these, but it's very difficult to create a device that has a very large range. Because if you have something that's sensitive to small sounds, to very low intensity sounds, then it's not going to work for higher intensity because that would basically destroy the device. Oh, where'd it go? What happened? I went to a web page. Sorry. There we go. So very extreme range, and very few of our detectors can do that. Now, because the sounds we detect, the sounds that we can detect cover such a large range, we have to have a special system set up to measure those. And this is where we get into decibels. This is called a logarithmic scale. It's a mathematical term. It just means factors of 10. All right, we can detect these very low sounds, these very quiet sounds, and then also these very large, these very loud sounds. And so we have to have this scale that's based on a logarithmic scale. And the logarithmic scale, you've probably seen logarithms before. It's probably been years since you've seen them. But a logarithm, it's on your calculator. You have a log. The log of 10 to the 0 we would call 0. And this would be the same as log to the 1. So if you want to know the logarithm of 1, you put in your calculator, you're going to get 0 out. And it comes from the exponent of this 10, because 1 is same as 10 to the 0th power. The log of 10 to the first power is equal to what, do you think? What is it? It's equal to 1. Yeah, so it's just the exponent. And 10 to the first power is just 10. So this would be the same as log to the 10, log of the 10. Log of 10 to the second power is going to be 2, and that's going to be the same as log of 10 squared, or 100. All right, I think we'll stop there. We're going to talk about decibels next time. I know this first bit is kind of dry, but we're going to get into some pretty cool things with waves, so y'all just hang in there. You can probably, well, I'll put the homework up hopefully today or tomorrow, so y'all can go ahead and start taking a look at it. As I said, your quizzes, I'll get back to you next week, hopefully on Tuesday, almost certainly on Tuesday. Don't forget to bring in food items, so that'll be March 25th. But that's next Tuesday, but we're not having class on Tuesday. Now, you can always bring them to my office. Actually, that's next Monday. I'm not right. Yeah, 510. Okay. Y'all do that. We have almost 100, so we need about 100 more. On average, if everybody brings 5, that'll be enough, because we have 60 people in this class. Y'all have a good day, okay? Y'all know where my office is in Beauregard, 139? Yeah, leave your name on them and leave them by my door. There's a box in there. Don't put them in the box. Just leave them by my door. And send me an email, too. That'd be great. Karen, do you know how many you have?